Good day, everyone, and thank you for joining us today. So today's topic is glass fiber reinforced plastic pipes, GRP or FRP in underground piping. As seen on recent projects, owners are not always aware of the benefits of applying glass fiber reinforced plastic pipe systems. This means opportunities to utilize more cost-effective materials may be missed. In this webinar, our subject matter expert, Chris Woltering, will explain the best practices of designing and constructing with GRP and why GRP can be a good alternative to traditional materials. Chris, we're really glad to have you here with us today. As is tradition, Chris will now set the stage for today's webinar by delivering the health, safety, and environmental topic before moving into the main presentation. Take it away, Chris.
Thank you, Ellie. As maybe some of you might remember, there was in 2004 a massive gas pipeline explosion close to a small industrial area in the city of Gellingen, Belgium. The situation sketch gives an idea of how close the crater of the exploded pipeline is to an existing building. So what happened that day? The DN1000 pipeline was in maintenance. Therefore, the pressure was reduced from 80 to 50 bar. At site, there were excavation activities going on for site finishing. Therefore, the soil cover on top of the pipe was decreased. During these excavations, the pipeline got damaged, but not noticed. Investigation afterwards demonstrated a wall thickness reduction of about 75%. When the pipe maintenance works were finished, the pipeline was put back to pressure of about 80 bar. Soon there was a smell of gas. At site they alarmed the fire brigade. The fire brigade arrived and a few minutes later the pipeline explodes. The damage was really a disaster. 24 people died, 132 were wounded, and there was nearly 30 million of damage to private property, like cars, etc. To give you an idea of the size of the crater after the explosion, it was about 14 by 14 meters wide and about 4 meters deep. And to give you an idea of the enormous power generated by the explosion, the pipeline section was found about 150 meters away from the crater. After this disaster, several countries started to develop regulations. If you look to the regulations in the Netherlands, the Dutch government developed several acts in which the following requirements are stated. First of all, there is a legal obligation to perform a so-called click notification at least 3 days before the excavation work starts. CLIC stands for Cable and Pipe Information Center. The installation contractor will receive latest info about all underground objects in his working area. Secondly, the network owners need to keep the piping network information up to date and submit after this click notification accurate information. Furthermore, the click information shall be available at site at all times. Any deviation found by the installation contractor of the actual position of underground services shall be reported back to CLIC. Also in the branch itself, related guidelines like the CROW guideline for proper execution of excavation works are issued. But despite this set of regulations, the situation is that still every week, at least in the Netherlands, somewhere there is a smaller or bigger gas line damage due to excavation works. So my safety message for today is: damage can happen everywhere, so investigate before excavate. The main topic of this webinar will be our experience with GRP piping materials. But before we touch upon this, I would like to explain briefly how our underground piping team looks like and which specialized engineering activities we perform on projects. We have a mix of experienced engineers and designers. Within this team, we are taking care of all design and engineering aspects of both pressure as well as gravity sewers and drain systems. Next to that, we are taking care of the space management of other underground items, including cable systems. So what are, in general, the underground design activities performed within our team? First of all, we develop design specifications for underground piping and sewer systems, especially when the client has no own specifications available, or if the scope of work is not completely covered by the existing specifications. Secondly, we develop standard drawings and we perform layout studies, normally 2D based, but sometimes also already 3D based. To confirm sewer diameters, we perform hydraulic calculations. And to confirm pipe wall thicknesses, we perform simplified stress checks. At the end of the design phase, combined underground plans and isometrics are developed and issued for construction to the installation contractor. On request, field support is provided, and support can be provided for the development of as-built drawings. Next to that, our team develops own documents, but we also provide input to documents developed by other teams, like a drainage philosophy, process instrument and diagrams, and the general pipe material specification. Besides our general activities within Fluor, we have specialized in design and engineering of non-metallic pipe material, especially glass fiber reinforced plastic. Glass fiber reinforced pipe is normally abbreviated as GRP or FRP, although you will find sometimes other abbreviations too. It is a composite material consisting of a polymer matrix and glass fibers. Sometimes extra sand filling is added in the core of the wall. The polymer matrix is usually an epoxy, vinyl ester or polyester thermosetting resin. Thermosetting means when cured by application of heat and or chemical reaction, it changes into a substantially infusible and insoluble material. The resin brings the environmental and chemical resistance and is the binder for the glass fibers in the structural laminate. The glass fibers, normally E-glass, add strength to the composite. Next to the structural wall of the pipe, there is normally a resin-rich liner for additional chemical resistance applied. In some cases even a thermoplastic liner is required. On the outside, a surface layer with UV inhibitor can be applied. Joints are typically made by means of lamination, by adhesive bonding, by balance spigot, with rubbering or a flanged connection. According to commonly used codes like ISO standard 14692, the vendor shall set up a testing program to qualify his products and shall justify and declare the product's mechanical and other properties for further design and engineering. In general, polyester pipe is used for the lower pressure, large diameter pipe systems, like a cooling water system. Vinyl ester piping is normally used for surfaces where a highly improved chemical resistance is required, like for example a chemical drain system. The epoxy piping systems are normally used for higher pressure and higher surface temperatures and or improved chemical resistance. Of course, final process and installation conditions will determine the most suitable type of composite to be used. Looking at our current design and engineering and installation experience with GRP, we have executed projects worldwide, from North America to the Middle East and from Europe to Asia. In the last 10 years, we have engineered, shop inspected, and supervised installation of more than 300 kilometers of GOP pipe systems, underground as well as above ground. These were pressurized water systems as well as gravity chemical sewer piping systems with pressure ranges from 0 to 16 bar and temperature ranges from ambient to 85 degrees Celsius, and diameter ranges from the small bore DN25 to the large DN2400. And last but not least, there is experience with several types of resins like polyester, vinyl ester and epoxy. Talking to GRP experts, there are several advantages of GRP. As GRP is chemical resistant by nature, it is a preferred choice in applications where internal corrosion is a major concern. This resistance extends to various chemicals and environmental factors, unlike, for example, HDPE, which is not resistant to hydrocarbons, and unlike steel, which can corrode and degrade over time and is sensitive to microbiological induced corrosion, also known as MIC. GP materials are significantly lighter than steel, resulting in reduced structural requirements for supports. Furthermore, GRP is a non-magnetic material, making it suitable for applications where magnetic interference is a concern, such as in the electronics and in the telecommunication industries. Also, GRP has a lower thermal conductivity compared to steel, making it a better insulator. This property can be beneficial in applications where temperature control is critical. GRP is a good electrical insulator, preventing electrical currents from flowing through the material. This characteristic is useful in applications where electrical insulation is required, such as in the electrical and electronics industry. Due to its corrosion resistance and long-lasting nature, GRP materials require less maintenance compared to steel, resulting in reduced maintenance costs and downtime. GRP can be easily molded into various shapes and sizes, and adjusted and reinforced in the field, making it suitable for customized applications where specific designs are needed. The lightweight nature of the GRP makes it easier to handle and install compared to steel, resulting in lower installation costs. Also, GRP materials have a lower environmental impact compared to steel, as they require less energy to produce and have a longer service life. While the flow resistance of the pipe is typically close to that of steel when the pipeline starts its operational life, due to corrosion effects, the flow resistance increases for steel piping, while it stays unchanged for GRP. Although there's more effort to be spent during the design process and during installation, there's more supervision, more critical reviewing of engineering documentation. It will give you less effort once installed. Call it fit and forget. It shall be noted that each material has its specific advantages and disadvantages, and the choice to select GRP will depend on factors such as application requirements, costs, and material availability. Of course, GRP has its limitations and disadvantages too. Looking at the temperature in general, it is limited to about 150 degrees Celsius. Also for the pressure, there's a certain limitation compared to steel. Although, as GRP is in a lot of times used in water systems, the pressure in underground systems is normally limited to about 16 to 20 bar, which is easy to handle. Where for HDPE, for example, these pressures become a challenge, certainly with elevated temperatures. What we see as disadvantage is the fact that GRP is a non-standardized product, meaning there's more effort to be spent during the design and installation. A more detailed review of engineering documents that are mainly produced by vendors is required. Also during production, it is advised to include shop inspection. Questions like, is the agreed testing scope executed by the vendor to qualify the products? Or does the vendor fabricate the components according the agreed fabrication drawings? Also during installation, it is advised to perform site supervision. Questions like, are all installation contractors, workers qualified, and is the piping installed according to vendor's instructions? Or is the backfill and compaction performed and tested in accordance with the project specifications? Also, additional attention shall be paid to so-called vendor-to-vendor connections, meaning you need to make sure a proper joint can be made from one product to another. Within the Eurocode environment, there are discussions going on about extending the design life from the standard 20 years to 50 or even 100 years. For example, for thermoplastics like HDPE, this standard is 50 years as per the codes. For new GOP pipe systems, it will be a matter of extending in a proper and acceptable way the regression line to at least 50 years and then determine the failure stress levels. For existing GP pipe systems, to determine the lifetime extension is also a must, as we see more and more clients asking what the current status of their pipe system is, and if and how the design life can be extended. There are, however, no reliable method yet captured in codes and standards to determine how much a pipe system is damaged during its service lifetime. Basically, there are two methods for damage, or so-called degradation. The first one is a creep-like behavior, micro-crack initiation and growth of these cracks by mechanical loads, like for example pressure. The second one is the degradation of the chemical bonding between the glass and resin by, for instance, water ingress or diffusion into the laminate. Knowledge about this is limited at this moment, and the degradation mechanism will not be activated instantaneously. Furthermore, the rate of degradation is also an unknown parameter. From a performance-based perspective, at the end of the initial material design life, it is difficult to assess what the progress of these mechanisms during the plant lives has been, and what the remaining life in the material is. Is redesign an option? Well, this would mean we need to go back to square one and redesign for a design life of 50 years instead of 20 years. This would only make sense if we have reliable records of 20 years of loading, mainly pressure and temperature, if these are available. Furthermore, full material regression reports shall be available that allow for determination of a 50 years failure stress level, and in particular for the diffusion related issues like water ingress. This large extrapolation from 20 to 50 years still introduces some uncertainty. For the mechanical loads applies that if during the 20 years of exposure they have not crossed the 50 years threshold, it could be decided that 50 years would also have been okay. On the other side, various end users and also vendors have applied short-term tests on excavated pipes that were exposed to 20 years of design loads, or sometimes even longer. In general, these tests show no degradation of the mechanical properties. So what we see is that developments are going on, and we might expect in one of the following revisions of the standards a section that addresses lifetime extension. So Why does Fluor think GOP know-how is beneficial? First of all, we saw more and more clients were asking for use of GRP in various types of pipe systems, instead of using the traditional materials like steel or HDPE. Fluor recognizes the general advantages of the material, but we also face challenges, for example, with the fact that GRP is a non-standardized product. Each vendor has his own fabricate. We also face challenges with understanding the content of the ISO 14692 code. Questions like how to practically apply the code in design or for performing stress analysis, or to understand what we can expect from GRP manufacturers and installation contractors. Furthermore, to understand what the type of testing that can be expected from manufacturers to demonstrate the quality of their product, and to understand the background of certain mechanical parameters used in design and engineering of components. Also, we face challenges with material selection for early material requisition. Shall it be polyester, vinyl ester, or epoxy-based composites? And finally, we wanted to also become more familiar with end-to-end dimensions of fittings, as there are vendor-dependent 3D modeling and space reservation can be sometimes challenging, especially when the vendor is requested to fabricate outside his standard products. To become more familiar with the background of certain GRP-related codes and standards, we joined since 2017 as one of the few EPC contractors several GOP working groups of the International Standards Organization, the European Committee for Standardization, and the Royal Netherlands Standardization Institute. We are especially interested in ISO 14692, which is a lot used in the petrochemical industry. Participants of this working group are major GRP vendors, GRP consultants, and certifying bodies from all over the world. Being part of these working groups gives us the opportunity to learn more about the material itself, to learn more about the background of certain subjects addressed in the standards, and furthermore, we are up to date about the latest developments, and we can have influence on subjects during revision work of these standards. I can tell you that ISO 14692 is currently under revision. Although not every subject is part of revision, with this new release the industry can expect a code that is easier to understand and to apply for manufacturers, designers, and installation contractors. Now let me share some best practices we have developed and adopt for GRP design and engineering, shop fabrication, and installation. Let's first look at key items during design and engineering. At Fluor, we aim to minimize fitting-to-fitting connections to limit stress concentrations. It also lends to simple installation requirements and saves precious project schedule. I've seen project schedules slip for pending vendor details, especially when vendors were requested to provide products outside of their standard. At Fluor, therefore, we try to stick as much as possible to vendor standard products, not in the last place, because we have the dimensions then already available, which allows the team to proceed with 3D design and model development with a calculated risk. Another best practice is to consider a minimum soil settlement, for it is one of the primary factors which can lead to unwanted or unexpected additional stress. I would highly recommend to use it at valve box connections and at underground, above ground connections. And finally, a best practice is that design should also account for the so-called F3 factor to allow for additional non-pressure related stresses. Reference is made to ISO 14692 for some default values. Now let me share some shop inspection and installation best practices. I can overemphasize the importance of having a kick-off meeting with the vendor and shop inspector to check the format and content of design and fabrication documents to be produced by the vendor, and if all test requirements are addressed and understood, and also to address the batch delivery sequence to support the construction schedule. Often I have heard site works getting delayed if the installation contractor brings too few jointers, or if there is an issue with jointer certification and qualification. Therefore, it's important to have a clear agreement in place in the contract on the type of bonders, training to be provided, and the number of bonders that will initially be certified. Although we strive to control conditions at site, we must be prepared for unexpected conditions. Therefore, a field inspector assignment should be undertaken with care, as an experienced field inspector will be able to have a critical look and act as eyes and ears for the construction supervision team. He will be able to describe the issue and to help troubleshoot the problems along with design experts. One aspect which is often undermined is backfill and compaction around the pipe system. At Fluor, we provide clear instruction to the civil contractor of the expected compaction levels, especially underneath the piping and in areas that require special attention. I would even recommend following up at site with proper field inspection of these works to avoid any nasty surprises in the future. Executing multiple GOP projects with sometimes help from third-party specialists, the many shop visits during GP pipe production we did, and the additional attention during installation and testing has widened our knowledge about GRP and has led to some subject matter experts for glass fiber reinforced plastic pipe systems within Fluor. We currently have subject matter experts in the fields of material selection, pipe system design, and in preparation and reviewing of surge and stress analysis calculations for GP pipe systems. At any project, there could be a certain type of damage to the GP pipe systems. Sometimes damage occurs during construction. For example, adjust buried pipe systems get damaged by new excavation works, or during a hydro test. It could be that the test pressure for some reason is exceeded, or that a pipe section is not properly supported and will see maybe unexpected bending stresses. Also, when commissioning or taking the pipe system, a service is taking place outside the design window could lead to damages. It's logic that any damage to a pipe system gets repaired in a proper way as per pipe manufacturers' recommendations. Over the years, Fluor has built up experience with preparation of root cause analysis and repair work. Root cause analysis is normally split into sections that describe the design condition. For example, it could be that loads are not addressed in design, like an unburied hydro test case or any additional differential settlement that comes up. Another section should be about materials. This to investigate if there has been any poor shop fabrication work. Another section should be about installation. Could be unexpected additional settlement due to backfill and compaction works, or there is poor installation and lamination work delivered by the installation contractor's crew. A last section could be for operation, in which there could be described that the client is operating the pipe system outside the design window. With the preparation of the root cause analysis and repair work, we have been assisted by GOP specialists for GOP sample investigation and additional laboratory tests. And as a result of the RCA recommendations, a certain type of repair can be determined. This can vary from adding some new and extra reinforcement material up to a complete replacement of pipe sections. We see our current GOP experience and the best practices we developed as a benefit because of the fact we can have a better understanding of our client needs and because our knowledge of the GOP codes that will help to understand what we can expect from vendors and installation contractors. Also, for our participation in co-development, we see that as a benefit. And with our expertise, we can manage complex GP designs and solve any related technical challenge. And last but not least, we see an in-depth market knowledge and we're having good supplier relations. Now we have come to the end of this presentation. I would like to leave you with a few key takeaways. First, we are convinced when you pay sufficient attention to engineering and installation activities, GOP pipe is suitable for multiple applications and is commercially a good alternative. Secondly, Fluor has subject matter experts for design, material selection and stress analysis. We do have an in-depth market knowledge and good supplier relations. Fluor has, for example, a close cooperation with GOP experts for root cause analysis and damage sample investigations in the laboratory. Furthermore, we manage a complex GOP design and solve technical related issues. And finally, we have a great experience with procurement of large quantities and with the selection of the right installation contractors qualified for the work. I would like to thank you for your time today. Now I will turn it back over to Ellie for any Q&A.
Thank you so much, Chris, for this extensive presentation. All right, we have had several questions that have come in. The first is, how is the FRP joint efficiency and are there repair sleeves available? So kind of two questions in one.
Well, basically the joint procedures are developed by the vendors, so they provide a method statement according to which the installation contractors have to make the joints. Does that answer the question?
Are there any repair sleeves available?
Prepare the types on the type of system you have, and repair normally is requested from the vendors in a dedicated document. So the vendor has to describe his repair procedure for a standard amount of, let's say, damages, and on request we can ask any vendor to produce a site or damage specific repair procedure. That is our experience. They will even come to site sometimes to get and help resolve the issues.
Okay, thank you, Chris. The next question is, what is the maximum pressure and temperature that these FRP pipelines have been used for, and the flexibility of the service fluids?
Well, there are developments going on, but what I try to explain that when you look at the temperature, it's in the order about to 150 degrees Celsius at least, and for pressure it really depends on the type of composite and surface that is used. It can easily go to a few hundred bars for certain applications, but what we see normally in underground piping design, so for cooling water systems, fire water systems, potable water systems and the like, they are normally restricted to about, let's say, 16 bar, and that is normally easy to handle by any type of GOP material.
Thank you. Next one is, do Do you have any experience with hydrocarbon transportation in GRP pipes?
Yes, we do. Although normally what we see in, for example, sewer systems, it's a combination of, let's say, stormwater and a hydrocarbon spill. But when you go to the so-called drain or closed drain systems, they can take easily the all kinds of hydrocarbons and drain it towards a vessel or a dedicated pit. That is no issue for GOP.
All right. So the next one is, what are the main issues in application of GRP for underground fire water systems?
Well, I would say normally there is no specific issue or risk related to firewater systems. It is all about getting the right product from the vendor, applicable for the process conditions, and furthermore a correct installation by certified workers of the installation contractors. Although we have to deal with the connection of hydrants and monitors, for example, which can impose additional forces to the pipe system. So for these type of connections, additional measures like concrete blocks or the like need to be considered to keep the system stable and avoid any additional stress issues that might damage the pipe system.
All right. Next, do we normally leave to the vendor or to an external engineer specialist the stress analysis?
Well, within Fluor, we have developed the expertise ourselves that as soon as we have the vendor data and especially the mechanical properties available, we are able to perform stress calculations and determine stress recommendations. But how we see it in general is that an EPC contractor provides a preliminary routing of the pipe system, including so-called stress isometrics, to the GRP vendor, and the GRP vendor will perform a stress analysis. And often the GRP vendor itself is also assisted by a dedicated engineering company. So then the vendor is asked to perform a stress analysis and furthermore to provide final IFC isometrics ready for installation.
Thanks, Chris. How is the GRP pipe connected to a concrete sump, and what measures are to be considered for leakages?
Well, normally when a GP pipe ends in a concrete sump, let's say for example in a sewer system, then you have several options. You can cast the pipe directly into the concrete, which means that the pipe section that is cast into the concrete is executed as a so-called puddle flange, which is there to avoid leakages during the curing of the concrete around the GOP material. You can also provide an oversized box or drill an oversized hole and use so-called seals like a link seal or a Doima seal to fill the gap between the outside of the pipe and the inside of the concrete pipe wall and make it leak tight. Furthermore, then you need to realize it might be somewhat more difficult just outside the pit to perform proper compaction, and that could be solved by, for example, applying a cement stabilized sand material which is easy to pour in and is more or less compacting itself. So in this way you minimize the settlement of the soil underneath the pipe, and you minimize any additional stresses close to the pipe wall inside the close to the concrete sump wall in the pipe wall.
Thank you, Chris. So the last question, Chris, is how is the workforce for skilled certified installers of GRP?
Well, normally an installation contractor has to get his workers certified for, let's say, the type of material, the vendor, and and moreover the project location where the project is executed. So what you see that is that normally the installation contractors are first asked to inform us what experience they have, if they have experience with vendor X or vendor Y, and if they have experience with the location where the work is going to take place. But ultimately, the vendor of the pipe material shall, for the non-qualified workers, arrange a bonders training in which the workers learn how to make a proper laminate or make a proper adhesive bonding, and to certify their test piece will be tested against a certain pressure so that the bonder can get his certificate and starts working in the field on the material where he's certified for.
Thank you, Chris. All right, I think that about wraps us up today because we're at the top of the hour. So I want to thank you, Chris, for the informative webinar and the time you've spent today and preparing for this. Thank you to our audience for attending today. It's been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on Fluor.com or following our social media channels using #InnovationBuilders. If you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention and thank you again for dialing in today. Again, if you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. From all of us on the Innovation Builders team, have a safe day.